In this video, we're going to discuss gas laws. So what are gas laws? Well, the different states of matter behave differently. A solid is kind of easy, it just sits there. And so we can put it on a scale and we can weigh it and maybe even measure it if it's got a reasonable shape. Liquids, they take a little bit more work. You got to make sure they don't fall and spill, but for the most part, you can contain them in a beaker and you can still weigh them and do things like that. Gas laws, on the other hand, come about because gases are not nearly so nice. They spread out. You can't keep them in a container unless that container is sealed. In fact, working with gases is rather difficult. You have to have completely sealed systems that store them, tubings and piping to connect them, and collection chambers to react them. As a result, it takes a lot of work to work with gases. But beyond just the glassware and material requirements, gases behave differently. They expand, they spread out, and as a result, they exert something we don't think about for the other materials, which is pressure. Now, pressure is going to have its own video, but pressure is a force on an area. So try this. Push your hand on a table and lean your weight on it. Most likely, you're probably able to take your weight on that hand just fine. Do it again, but this time, use 2 fingers, just the tips of your fingers, and lean on it. It starts to hurt, most likely. The reason is you're leaning exactly the same amount of weight down on it, but when you had your hand had a very large area. There's a lot of surface here to spread the weight of your body out over, but when you just had 2 fingertips, all that weight was on a much smaller area. Pressure is a force over an area. So force, a mass being pulled by gravity, is a force. It's got a impact and a push that you can feel. How big that area is changes the pressure that is applied. And so your fingers probably hurt a lot more because the pressure on them was much greater than it was on your hand when you could spread the weight out over a larger surface. What this really plays out to in terms of materials is if I have a container and it has some gas in it, that gas is bouncing around. It's hitting the walls. It's bouncing off things. Those walls are being pushed. As far as the wall is concerned, it feels a shove out. The gas inside is pushing it out all the time. This is why when you have a Coke bottle or anything like that, if you shake it up aggressively, it kind of bloats. Or if it sits in the sun, it starts to expand a little bit. Or if you just have a new bottle, it's very hard to squeeze them. But if you've opened it and let the pressure out, they squeeze much easier. The gases are literally pushing out all the time because they have a pressure. This is something that, well, you can have for liquids, only comes up if you're under the liquid. The liquid sitting in a open bowl or even a sealed water bottle isn't really exerting a pressure greatly on the walls. It is some, but not like the gas. And so we'll dive pressure more in another video, but this becomes critical for gas laws. Because of this difference in behavior, we can't really follow them the way we follow liquids and solids. So there's a lot of interactions that come about from this, but we're going to jump to the final component of them all, the ideal gas law. The ideal gas law says that my pressure, so P for pressure, my volume, V for volume, is going to equal my moles, which we write as N. So back when the gas law was made, number, I guess, was the idea, but N is moles in our case. R is just a constant. It depends on what our other units is. It's just designed to balance size scales. So we'll give you some R values for those constants soon. T for temp. So I've got my pressure, my volume, my moles, my gas law constant R, and my temperature. These all relate to one another in order to be necessary to talk about how much gas there is, what is the temperature of that gas, what kind of space is it taking up, and how hard is it pushing on the containers that it's in. So where do they actually come from? Well, why do we care about those things for gas laws? Let's think about a cylinder. So I've got like a car engine cylinder, it's got a piston, and there's some gas. Now that gas bounces and hits the walls, and it hits so many times per second, and there's a big area for it to hit. But if we push that piston down, it compresses the gas. Those same gases are now in a smaller space, and traveling at the same speed, they're going to hit the wall more times per second. Basically, the idea is if you have two walls, and you can travel from one to the other in, say, 1 second. So you'd have 1 hit per second on each wall. Well, if my distance is just half as far, I'll hit one wall and I'll bounce back. So now I've hit the wall twice as often in the same amount of time. If you got hit twice instead of once, you got hit with twice the total force. By compressing our container, we force the gas into a smaller volume, and that means it hits the walls more often. The net result is that if our volume goes down, our pressure goes up. How often we're hitting those walls increases. This is an inverse relation to each other, but this is necessary to understand how much force that gas is pressing. If you have a smaller container, the gas has to travel less distance to hit the wall, and therefore hits the wall more often. And back to our pressure is force over area. If I hit the walls more often, then my force is greater. Or conversely, if I reduce my area, force for a smaller area results in a larger pressure. So either I'm hitting more often or there's less to hit, but either way, my pressure goes up. And so volume and pressure are related for a gas, and that's why we need to know both of them to talk about, well, what's the gas doing? How is it behaving? If we think about things like, let's say I have a container and it's got 3 gas molecules and they bounce around so often. Well, if I have the same size container but it has twice as many gas molecules, there's just more things hitting the walls. So I'll have 6 things hitting the walls instead of just 3 things. The net result is, by having more stuff in the same container, there's just more impacts on the wall. So really what I had was my volume stayed the same in both these cases. I had some pressure and I had some moles. As my moles went up, my pressure goes up. And so as I got more moles in my container, they just collectively hit the walls more often. And so the total force is increased, even though it's the same area of the container, and thus my pressure looks like it's higher. And I mean, it is higher. You're hitting something more often. One way to view this type of thing is if you threw a tennis ball and you hit a window, it'd shake a little bit and probably wouldn't break. Please don't try this at home. But if you threw 30 tennis balls really fast, well, you might actually succeed at getting it to shatter. Like, it's just getting hit too often with too many things, and it doesn't have time to recover or stabilize. Getting hit more often increases the force that is being exerted on that object. So we can see how moles can factor in a little bit. Other ways to think about this is, what if you have a balloon? Well, our containers over here didn't change size, but a balloon, the whole point is balloons get bigger if you put more stuff into them. You breathe in once, it goes from a small balloon to, actually having some gas in it. You breathe in again, it gets bigger. This is an idea of volume and moles. As my moles goes up, my volume also goes up. So a balloon is actually an interesting idea. If I've got a container that can stretch, well, when my gas molecules hit the wall, it pushes that wall out. And so as my gas bounces around and hits the walls, it's actually shoving the walls of my balloon out. The result is they move, they stretch, they get bigger. But the bigger it gets, the slower or the longer it takes my particle to hit the walls. And so they stop stretching as much. The outward force goes down. As a volume gets bigger, the pressure goes down, which we looked back earlier, it's just the reverse of our earlier statement. So the balloon, as it starts to get bigger, the pressure decreases. But as long as there's anything pushing something, it'll keep moving unless you can put a counter push on it. I don't know if anybody's had older or younger siblings, but if you ever did the thing where you put a hand on their head and they pushed at you and you held them back, if you put an opposite force, it just counters the movement. Well, there's gases outside. There's a bunch of gas in the atmosphere, and those gas molecules are hitting the balloon. They're bouncing off of it. So there is an inward force on a balloon. So if I have a balloon, there's an inward force coming from the outside, and there's an outward force coming from the gas on the inside. If we find that the total on the inside is greater than the outside, then our balloon gets bigger. But because expanding the balloon decreases our inside, eventually our outside gas will match it. It'll drop until it matches the outside pressure. Neat effect is then that our balloon, the pressure inside a balloon is always equal to the outside pressure, whatever just the atmosphere itself has. So if you try to balloon up in space, it just kind of keeps getting bigger until the elastic breaks or maximizes its stretch. But down on Earth, and if you've ever gone up a mountain or something, you may have seen this. If you have a balloon blown up at low elevations, you go to high, it expands. If you ever had one at high elevations and you go low, it contracts. It will adjust its size so its inside pressure matches the outside. So this is pressure, volume, and moles and how they relate to one another. Let's think about temp. If I've got a container and it has some gas in it, well, as I heat it up, same container, so my volume is constant, so no change in volume. My moles is constant, no change in moles. What I do have, though, is pressure and temperature. Temperature is a measure of the kind of average kinetic speed, or at least it's related to it. So the faster your particles are moving, the higher your temperature. Well, if you're moving faster, you will hit the walls more often. If you're moving slow, you only hit those walls a couple times, but if you're moving faster, you can hit them a lot more. More impacts means more force. So as my temperature goes up, my pressure will also go up. And so our pressure and our temperature are actually related to one another this way. Similarly, if I have balloons with some starting materials, well, as my temperature goes up, they'll move faster. They'll hit the walls harder. As a result, they'll increase in size until it takes them so long to hit the walls that the pressure matches the outside. And so what happens is my temperature goes up, my volume will also go up. All of this can combine into one nice relation, which is pressure volume equals nRT. And so we're going to talk about the units that we use in gas law practices, but this is the idea of some of the properties of a gas. How do they relate, and what is it we need to have the ideal gas law?